So, very good evening and welcome to the fourth session of the course Power Plant System Engineering. We are doing module 2, that is Vapor Power Systems, part 2. Okay, so let me share the screen and then we will wait for a few more minutes. Okay, my screen would be visible. Let's wait for 2 more minutes. In the meantime, anybody can join. Okay, so that's the time, and I think I should go to the slides. Hmm. I will keep the meeting open so anybody can join in the meantime. So here are the things. It is the fourth session of the power plant system engineering. Okay. And yeah, here are the topics covered in the past week. We'll summarize these topics and then solve the quiz problems. Let me check it. Okay. So the topics covered uh, in the past week are the rotodynamic machines, impulse turbine, velocity diagrams, impulse turbines, single stage impulse turbine, compounded impulse turbine, then velocity compounding impulse turbine, and pressure compounding impulse turbine. Then we have seen the reaction turbines, velocity triangles, and optimum operating parameters, in which we have seen the power output, blade speed, nozzle efficiency, moving blade efficiency, and stage efficiency. So all these efficiency we will look into the formulation and what does they means. Okay, and lastly we have seen the comparison of a reaction turbine and the impulse turbine, and then we have solved some tutorial problems. Okay, next the aim of the session would be the same, to give quick summary of the topics covered in the past week, to discuss the doubts if you have, and to solve some assignment and classroom problems. Okay, so this would be the aim. To start with, we will start with the rotodynamic machines. Okay, so what does a rotodynamic machine means? Rotodynamic machine. So in this kind of machines, generally the energy transfer takes place between any fluid stream and a rotor. Okay, there would be a fluid stream and a rotor. I will write the things first. Rotor and a fluid stream. So, if the energy transfer takes place from fluid streams to rotor, Then it is called the turbine, and these are the work producing device. If the energy transfer takes place from rotor to the fluid stream, then the examples could be fan, compressor, and pump. Okay, compressor and pump. So here the fan and compressor dealt with the gas and pump deal with the fluids. Okay, so these are the rotodynamic machinery. We can classify them as the axial flow or radial flow. Okay, so here in the uh, power plant engineering systems, our focus would be on turbine. Okay, as we have seen in a power plant, it has the pump, boiler, turbine, and condenser. The cycle goes like this. This is boiler, turbine, condenser, and pump. So here, this turbine is the vital part of a power plant, which converts the heat energy to the mechanical energy. And these turbines could have the types of axial flow or radial flow turbines. Here we will have a look at the classification as the impulse and reaction turbines. So in steam power plants, these turbines could be the impulse turbine, impulse turbine, and reaction turbine. Impulse turbine and the reaction turbine. So in the upcoming slide, we will have the formulation of these turbines. We will start with the impulse turbine. So impulse means that a force which impinge on a object for a very short period of time. So that short time force is called the impulse. Okay, let's first we will do the things uh, for a flat plate, jet impingement of the flat plate. Flat plate. So from this flat plate, we will learn the definition of the impulse. Let's suppose we are having this plate, okay, which is stationary or fixed plate. This is the plate. Jet is coming from here and goes like this. Okay, so jet is going like this. From here, it is going like this. So this is some sort of fixed plate. And second configuration, I will make it on a rotor. So this is the rotor. This is the rotor and jet is coming like this. Okay. So the jet will impinge some force on this plate. Okay. So here is the fixed plate. Let's suppose BV is the velocity of the plate. So as it is fixed, it would be 0. But here it is not fixed. It is also moving some velocity BV. Okay, and here the jet velocity will say Vs. Say just a notation. We have considered S is the jet velocity and Vv is the plate velocity. So here for the let's suppose this is a configuration A, this is a configuration B. Is someone there? Okay, still anybody is not there. Okay. So here we will first write the expression for the force on the fixed plate. Force on the fixed plate. The force would be the rate of change of momentum. This F would be the m dot into initial velocity is Vs, then the axial direction here the velocity would be 0. So ultimately it would be the m dot Vs. While the force on the moving plate, force on the moving plate, F would be m dot into, here it would be the velocity relative to this uh, plate velocity. So here the relative speed is Vs minus Vb. Here Vs is the jet speed and Vb is the jet velocity and Vb is the plate velocity. Okay, so work done, we know that the expression of work done would be the work done per time or work done rate. Work done per time would be, or we would say power, W dot is equals to this force m dot Vs minus Vb into the displacement in the unit time, and that would be the Vb. So the ultimately this expression would be W dot is equals to m dot Vb Vs minus Vb. Okay, and the initial power with jet consists of the jet initial power. Jet initial power would be initial power would be in the terms of the kinetic energy of the jet consist, K would be half into m dot into the square of the jet velocity Vs. So this would be the power which consist uh, which the jet consists. Okay, and this is the work done or rate of work done or power. So from here we could define the some variable parameters like the efficiency of the plate. Efficiency of the plate would be eta P is equals to rate of work done or power. It would be the ratio of the work done divided by the kinetic energy which the jet consists of. So what it would be, the W dot configuration we are having m dot VB Vs minus Vb divided by half into m dot into the square of the Vs. So when we will simplify this thing, then it would come eta P is equals to twice of this thing would come here. Okay, So H B. Okay. So this would be VB by Vs minus VB by Vs square. Okay. So here this would be the expression of the plate efficiency. Now our next aim would be what would be the optimum plate speed for the maximum efficiency. Now next question would be what would be the plate speed for the maximum velocity. Okay. So for that thing we have to differentiate and then put that to 0. So for that we need to do the things differentiation of NP with respect to the rate speed would be 0. So the expression would become 2 into 1 upon Vs minus 2 Vb by Vs square is equals to 0. Then this will become the optimum plate velocity would become half of the jet velocity. Okay. And when we put this value to the expression of the power, then W dot max would be the expression it is having m dot into Vs by 2 into Vs minus Vs by 2. So this will become 1 by 4 of m dot Vs square. And what is the expression this kinetic energy was having? Ke was having half m dot Vs square. So from here we can calculate the optimize the maximum plate efficiency would be the W dot max divided by Ke. So this value we are having for m dot Vs square divided by half m dot Vs square. From here, this maximum plate efficiency would be 50%. So it implies that by the help of this flat plate jet impingement, we can't generate, we can't get the efficiency more than 50%. So this is the maximum efficiency for the flat plate. And one thing we know that this is not a very high value. So next we will find the ways to enhance this efficiencies. Okay, so next we'll find the ways to enhance this efficiency. So next we will try the same things with a curved blade with the curved blade. Okay, so here we are having the curved blade and here we will check the same the power, the work done, the rate of work done that is efficiency and the blade efficiency whether we can have the higher value or not. So let's suppose this is my curved blade. Okay, and the jet is going like this and it is coming like this. Means this is going at the angle of 0 degree. Okay, and it is exiting at the angle of the 180 degree, and the blade is itself moving with the speed of Vb. Okay, and here the jet speed is Vs. Okay, and this is my inlet, and this is my outlet. Okay, this is my nomenclature, and here the same thing we will try to get the impulse force, the power, and the blade efficiency. Here we will say it the blade because we are having the curved blade here. So these three things would be the aim to calculate in this problem. Okay, so starting with the relative velocity of float jet at the entry, the relative velocity of float jet at entry, it would be the here the relative velocity would be Vs minus Vb. Okay, Vs minus Vb. Similarly, the relative velocity of fluid jet at exit, relative velocity of fluid jet at exit, it is having the similar value. It would be uh, this velocity would be Vs only, and here the blade is moving with Vb, so it would be the Vs minus Vb, the same value. While we will write the absolute velocity, then what would be the value? The absolute velocity at exit, velocity of at exit would be the blade velocity. So this is absolute velocity minus this relative velocity, Vs minus Vb. This value will come out to be 2Vb minus Vs. Okay, so this absolute velocity here will be 2Vb minus Vs. Okay, so the impulse force would be impulse force would be F is equals to rate of change of momentum. So final initial velocity is Vs minus final velocity is 2Vb minus Vs. So this value will come out to be 2m dot into Vs minus Vb. So this is the expression for the impulse force. Similarly, the power the power would be W dot would be F into blade velocity Vb. So the expression would be 2m dot Vb into Vs minus Vb. So now we are having both the values like this W dot, and we are also having the expression for the kinetic energy we know. This would be half m dot Vs square. Okay, these are three expressions. Now by the help of this we can determine the blade efficiency. The blade efficiency, what would it be? Eta b, we know that W dot divided by kinetic energy. So the expression we are having like m dot VB Vs minus VB divided by kinetic energy is half m dot Vs square. So when we simplify this value, this would be the 4 times of VB divided by Vs minus VB by Vs square. Okay, so this would be the expression for the blade efficiency. Now the next thing, our aim would be the same. We have to determine the optimum blade velocity. Optimum blade velocity would be what? For the maximum power generation or maximum blade efficiency. For maximum power. So we will do the same thing. We will differentiate the power with respect to the blade velocity and then will put it to 0. So here are the things dy dvb of 2m dot vb vs minus vb is equals to 0. It will come out to be 2m dot vs minus 2 vb is equals to 0. So here also vb optimum would be vs by 2. So for this optimum blade speed, the maximum power would be 2m dot into vs by 2 into vs minus vb is also vs by 2. So the expression would be 2 will be cancelled by this 2. So it would be half m dot vs square. Okay. So now the maximum blade efficiency would be w dot max divided by kinetic energy. So we are having this same value here, half m dot vs square by half m dot vs square. So it would be cancelled out. It implies that in the curved blade, the maximum efficiency could reach to 100%, while in the flat plate case, it was only 50%. So here it implies that if we use the curved blade, then this efficiency could be reached to up till 100%. Okay, so the next thing is that now at this entry and exit, now the case we have just discussed is that there the fluid is entering at 0 degree and leaving at 180 degree. So in the practical problems, it is not feasible, and we have to use the series of blades for the to enhance the power generation, and so that there would be some angles at the entry and exit. There would be some angles at the entry and exit of the curved blades. Okay, and these angles we have just seen. And to determine the impulse force, first we have to determine these angles, and then only we can determine the impulse force. So I will take an example of these angles. Okay, let me take another color pen. And in the same figure, you will understand the velocity triangle. Okay, like this is the single blade. I will make these horizontal lines. Okay, let's suppose blade is moving with velocity VB. At this velocity, the blade is moving. All right, and the relative velocity is VR, which synchronizes the Z velocity to this entry. This is the blade velocity V1, and this is the absolute Z velocity at the entry VS1. Angle between the horizontal and this jet stream is known as the nozzle angle theta. So here theta is the nozzle angle. Okay, and this angle between the horizontal and this relative velocity phi, this is known as the blade entry angle. Similarly, the at the exit the fluid will leave like this, and it will have this same blade velocity. So this is the relative velocity at exit VR2. This is the blade speed VB. It would be the same, and here it would be the absolute velocity at exit. So this angle, to say this angle is known as del. So del is the fluid exit angle, and this angle gamma. Gamma is the angle between the horizontal and this uh, VR2, the relative velocity at the exit. It is called the blade exit angle. So in the most of the problems, our aim would be to determine these four angles, then magnitude of different velocities. Then we would be able to determine the uh, impulse force. Okay, and every time you have to remember that uh, this in any case, VB plus VR, the blade velocity and the relative velocity would be able to the jet speed, absolute jet speed. The same thing we can see here. This VR1 plus VB is equals to VS1. This is the vector addition. Okay, this is the vector addition. So these are the things. And for this case, this uh, the horizontal component of horizontal component of Vs are called the world velocity. for the world. Okay, this thing we have to keep in mind. Okay, and so for this configuration also we will determine the maximum power and the optimum blade speed. Okay, so the impulse force for this configuration, we'll write for the impulse force. Okay, so impulse force for this component, this diagram, it would be the rate of change of momentum in the axial direction. So what it would be, I will write just the expression. F would be the mass flow rate into Vs1 cos theta minus Vs2 into cos tan. Basically, these are the world component at the inlet and the exit. World means Vw. So world component at exit is the Vs1 cos theta, and world component at exit would be Vs2 cos del. So this impulse force can also be written as m dot into world at inlet minus world at exit. Okay, so this is one expression. Now the power we can written as W dot would be F into VB. So the expression would be m dot into VB into Vs1 cos theta minus Vs2 cos del. Okay, and the expression for the kinetic energy we are already having half m dot Vs1 square. So the blade efficiency for this case would be W dot by Ke. So expression would be twice of Vb by Vs1 into cos theta minus Vb by Vs1 into Vs2 by Vs1 into cos del. Okay, so this is the expression. So here clearly we can see that if the del would be greater than 0, then cos del would be less than 0 negative, so that w naught w dot would be more and this component would be added. Okay, this thing we have to notice. Now from the same velocity triangle, when we apply some trigonometry, then we can write the things like that. This vr1 cos phi would be vs1 cos theta minus VB. Second thing we can write Vs2 cos del is equals to 2VB minus Vs1 cos theta. So these two relation we have to use when we will determine the uh, optimum blade velocity. So when we will put this expression in this thing, then we will get to know, we will get this expression as W dot is equals to M dot into VB Vs1 cos theta minus Vs2 cos del is equals to 2mVB V1 cos theta minus VB. Okay, so this is our final expression for the power. Based on that, we can calculate the optimum blade velocity VB optimum. So for that, what we have to do, we have to do the dw dot by dvb is equals to 0. I have already done this thing and got the expression it like the optimum blade velocity would be Vs cos theta by 2. This would be the Vs1 cos theta by 2. Okay. So when we will put this thing in the equation number 1, then the maximum power would be half m dot. Okay, this is the thing. This would be the yeah. So what it was the 2m dot VB into V1 cos theta minus VB. Okay, so the expression for the W dot max would be the 2m dot VB value is Vs1 cos theta by 2 into Vs1 cos theta cos theta minus Vs1 cos theta by 2. So the final expression would be the half m dot vs1 cos theta whole square, or it would be 2m dot vb optimum का square of 2m dot. Okay, and for that the optimum blade efficiency would be w dot max by ke, so it would be half m dot vs1 square cos square theta divided by half m dot vs1 square. This thing would be cancelled. So in this case, the curved blade with at theta angle, the maximum efficiency, the optimum efficiency would be the cos square theta, square of cosine of the nozzle angle. Okay, so this is another thing. There are a few more definitions I would write here, then we will solve the tutorial problem. Okay, few more definitions are: for the symmetric blades, for the symmetric blades, the blade angles would be the blade angles at inlet and exit would be the same. Okay, and if there is no friction, then relative velocity would also be the same for no friction. These are 2 points. And if we look at the thermodynamic view, then this generated power would be the enthalpy difference, summation of enthalpy difference plus the kinetic energy difference, vs1 square by 2 minus vs2 square by 2. Okay, and we know that this enthalpy difference would be m dot of relative velocity difference of the relative velocity kinetic energy, so that this w dot would be m dot by 2 vs1 square minus vs2 square plus negative of that negative vr1 square minus vr2 square. Okay, so for pure impulse, there's somebody waiting there. So welcome, and I hope my slides are visible. I'm just writing the formulas, and after that I will solve the assignment problem. Okay, so for the pure impulse, this uh, the relative velocity would be same, enthalpies would be same. So the power for pure impulse would be half of m dot into absolute velocity at inlet minus absolute velocity of jet at the exit. So this is the formula for power for pure impulse thing. Then we have other parameters like the velocity coefficient, velocity coefficient. This is defined as the ratio of the relative velocity at exit to the relative velocity at inlet. Okay, so this relation also we could use in the numericals. Next, the last thing is this: the stage efficiency is would be defined as the ratio of the power divided by the enthalpy drop in that particular stage. Okay, so this thing we also have to keep in mind. Then we have learned about the the types of impulse turbine. Okay, the types of impulse turbine, where we stages the velocity. Then this is called the velocity compounding, and when we stages the pressure, it is called the pressure compounding. Okay, then we came to the reaction turbine, where we defined the 50% degree of reaction turbine would be the Parsons turbine. So wherever in the numerical we got to see that the Parsons turbine. So by default, the degree of reaction for that reaction turbine would be 50%. And for that, for this reaction turbine, the optimum blade speed. Okay, okay, this not this is the optimum blade speed would be Vs1 cos theta, wherever in the case of impulse turbine, it is the half of Vs1 cos theta. Okay, and I think there's somebody there. Okay, and the maximum work done would be maximum rate of work done. Basically, the power it would be the m dot, the optimum blade velocity square of that. Okay, or it would be m dot Vs1 cos theta to the whole square. These are the things for the reaction turbines. Also, we have defined one thing, the enthalpy drop in the moving and static blades, and basically we divide it like 50-50%. Then lastly, we have defined the degree of reaction. Basically, this is the enthalpy drop in the moving blade divided by enthalpy drop in the stage. Okay, and basically, what do we mean by, okay, it's gone wrong. What do we mean by a stage? Is basically the, like suppose these are my blades. Okay, the reaction turbine we are not having the symmetric blades. So like these are the fixed blade FB, the non-threaded, and these are the moving blade MV. So this complete thing, one row of moving blade and fixed blade is the one stage. Okay. So the degree of reaction would be simply the enthalpy drop in this moving blade row to the total enthalpy drop in a stage. So this much was the theory we are having for this week, and I have I had kept it short because in each class we ran out of time. So here I will start with the assignment problems, and then if we will have time, then only I will do the classroom problem. Till then, okay. So what does this first problem said? If the energy is transferred to the fluid from the uh, rotor, then the machine is known as turbine. So this statement is not correct. In the first slide, I told that okay, here it is. When we when the energy supply takes place from fluid stream to rotor, then it is called the turbine. And when rotor to the fluid stream, then it is called either fan, compressor, or pump. So here the problem is saying that the energy transfer is takes place from fluid to from the fluid to rotor. So this machinery would be either okay. No, uh, transferred to the fluid from rotor. It is another way. Okay, so here energy transfer takes place from rotor to fluid. So this device could be a fan or a compressor or a pump. So this statement is wrong. So this is false. So B option would be correct. Next is in which of the following machines and energy is transferred to the fluid from the rotor. Okay, in the last scene, in the last problem, we have seen that in which of the following machines energy is transferred from to the fluid from the rotor to fluid. So in fan also, in compressor, or in pump. So all of the options are correct here. So not A, B, C. The D option would be correct here. Next thing is that the problem is saying like a fluid jet impinges in the positive x direction to the vertical plate. Okay. If the plate is allowed to move freely in the horizontal direction with a velocity Vb. So here this velocity is Vb and here it is freely allowed to move. The maximum efficiency of converting the jet energy to the plate it is. So here what they have asked, the maximum plate efficiency. What would it be? So actually this thing we have done in our slides. I will go to that only. Okay. So here I have considered the similar cases, the fixed plate and the moving plate. Okay, it is having some sort of roller here. Then the force on the fixed plate would be force would be the rate of change of momentum. So it would be the m dot vs, and the similar value of for force for the moving plate would be m dot vs into vb. The work done per unit time or the power could be written like this. We will multiply it with the VB only, and the kinetic energy is like this. Then we have determined the plate efficiency, like eta P would be the work done divided by the kinetic energy of the jet, which is coming like this, and the expression for the plate efficiency is this. Okay. So to calculate the maximum value of this plate efficiency, we have determined the optimum value of this plate speed VB. Okay, by differentiating the eta p with respect to the VB and then putting it to 0. The value of the differentiation is coming like this, and when we put it to 0, then the optimum plate speed is coming out to be VB optimum is equals to Vs by 2. Okay, when we will put this optimum value of plate speed in this equation, to precise, to be here, then the value of the maximum power is coming out to be 1/4 of m dot v square, and we are having the value of kinetic energy which z consists of is half m dot vs square. So when the maximum uh, plate efficiency would be the, I will write the values here. The actually it is solved previously, but the values it is having eta p max would be the maximum power divided by the kinetic energy of the jet. This value we are having 1/4 of m dot vs square. This value we are having half m dot vs square. So this maximum value of this efficiency is coming out to be 50%, which is coming out to be here. So here a D option would be correct. If you are having any doubt in this till here, then we can discuss. Otherwise, we will move to the next problem. Okay, so our next problem is, in the case of cylindrical blade that allows the jet to reverse its direction, the maximum blade efficiency is 200%. So we have to tell whether this statement is correct or not. Actually, what they are asking, they are taking the case of this geometry. Actually, we have also derived this geometry also. So it is coming out cylindrically like this at 0 degree and reversing its direction at the exit. So this part is inlet and this part is outlet. Okay, the blade is coming Vs like this. Blade is moving by the speed of Vb. And what we have to tell here, we have to tell the maximum blade efficiency, what value it would consist of. So we have done this thing also previously. Actually, I would write here it is solved in previous slide. Okay, and where it is, I will just quickly show what we have done there. Okay, so this is the case. We have considered the case of the curved blade. The jet is coming, going like this and coming like this. This is inlet, this is exit, and here Vb is the blade velocity. So here the relative velocity of the fluid jet at the entry, it would be the Vs minus Vb. Actually, we are sitting on this blade, and from there we are observing the relative velocity. Similarly, the relative velocity of the fluid jet at exit, it would be the Vs minus Vb. When we talk about the absolute velocity of the jet, then it would be the Vb minus Vs minus Vb. The value will come out to be 2Vb minus Vs. The impulse force would be F is equals to rate of change of momentum. So Vs is the initial velocity and 2Vb minus Vs is the final velocity. So the value of the impulse force would be 2 m dot Vs minus Vb. Okay. Then we have determined the power. Then we are having the value of kinetic energy of the jet as half m dot Vs square. Next, we have calculate the blade efficiency. It is the expression would be the W dot divided by the kinetic energy. Okay, so the value are coming like this. Now our aim is to determine the optimum blade speed for the maximum power. So for that we have differentiated this expression of the power with respect to the blade speed and then put it to 0. Then the differentiation is looking like this. When we simplified it, then we have got the optimum blade speed for the maximum efficiency or maximum power as Vs by 2. When we have put it this Vb optimum in the expression of the power, then maximum power we got as the half m dot Vs square, and similar expression we are having for the kinetic energy, that is half m dot Vs square. So like this we got the maximum efficiency as 100%. So here the from the previous slide, the eta b maximum would be W dot maximum divided by the kinetic energy. Both are having the same values, half m dot Vs1 square and half m dot Vs1 square. So it is having the maximum value of 100%. Okay, and here it is written 200%, which is intuitively it is not possible. So this statement is also false. I just wanted to show the how I have derived the things. So the next thing is a float jet impinges in the positive x direction to the vertical plate. If the plate is allowed to move freely in the horizontal di direction with a velocity Vb, then the optimum plate velocity that maximize the power is. Okay, so here we have to determine the optimum blade velocity which maximize the power. This thing we have already seen. For the flat plate, it is coming out to be, there is no meaning to solve the same things again and again. So we have seen that it is V optimum is equals to Vs by 2. So it is it is, or in other words, we can say that 50% of Vs. Which option is matching? Option B. So the optimum blade or plate velocity is coming out to be 50% of the jet velocity. Okay, so coming out to at the next problem, let's have a look at this and then I will solve for this thing. Okay, so this is the sixth problem, and what it is saying is that a fluid jet impinges on a cylindrical curved blade that allows the jet to reverse its direction as shown in the figure. As a result of this impingement, it includes the blade motion to produce power. Okay, if the uh, fluid jet velocity Vs is for 40 meter per second, then what would be the optimum velocity for the maximum power? So this thing we also have done. It is given that Vs is equals to 440 meter per second, and here in this slide we have seen that the optimum blade velocity would be half of the jet velocity. Okay, so just we have to apply this uh, conclusion there. So we know that Vb optimum is equals to Vs by 2, which is 440 by 2. It is 220 meter per second. Okay, so this B option would be correct here. In the seventh problem, what they have asked is that the things they have provided are the steam enters the nozzle of a single stage impulse turbine with a flow rate of 45 kg per second. I would write here the mass flow rate m dot is equals to 45 kg per second to produce a net power of 5500 kilowatt. W dot net is equals to 5500 kilowatts, and the enthalpy of steam at the inlet of the nozzle. At the inlet of the nozzle means H1. Here the inlet we are denoting by 1 and exit we will denote by 2. So here H1 is the this 3095 95 kilojoule per kg, and at the exit drops 2. Here drops 2 is written, so H2 would be 2950 kilojoule per kg. So here the enthalpy drop, we can write it as enthalpy drop delta H would be H1 minus H2. It is 3095 minus 2950 is equals to 145. So this is 145 kilojoule per kg. It would be 145 into 10 to the power 3 joule per kg. Now what they have asked, the blade efficiency in percentage they have asked. So by the help of this, we can determine the uh, nozzle velocity. We are having the expression Vs would be under root 2 into delta H. This is nothing but the enthalpy, the energy conversion, kinetic energy to the enthalpy. So expression would be 2 into, this would be 145 into 10 to the power 3. So Vs value we will get here 538.5, 38.5 meter per second. Okay. Next, we know that the blade efficiency is the net power divided by the kinetic energy. The net power is 5500 kilojoule per kilowatt. I will multiply it to 100 to convert it to the watt. Then kinetic energy would be half into m dot. M dot is 45 kg per second into this Vs square would be 538.5 square. Convert into the percentage, I will multiply it by 100. So from here, the blade efficiency will come out to be 38. It will come out to be 84.29 percentage. 84.29%. So here the answer for the blade efficiency is, choose different color pen. Answer will be 84.29%. Okay, so this would be the answer. Moving to the next problem. The eighth one, uh, they have asked for the stage efficiency. The problem was say they have asked the stage efficiency. Okay, so here they are saying the same thing. The mass flow rate m dot is equals to 45 kg per second. producing a power W net is equals to 5500 into 10 to the power 3 watts. Then enthalpy at inlet H1 is equals to 3095 kilojoule per kg. Enthalpy at exit S2 is 2950 kilojoule per kg. Okay. So the expression for the stage efficiency we have seen, it would be the W net divided by the enthalpy drop in the stage H1 minus H2. So this value will come out to be 5500. I will keep the values in kilowatt only. So 30 m dot. How can I forgot m dot? Okay. So m dot is m dot is 4500 into 3095 minus 2950. I will multiply it by 100 to convert into the percentage. So this value will come out to be 5500 45. The same value will come as the previous one because here we have considered no loss 84.29%. The same value would be here. Okay. So here also answer is 84.29%. Okay. So in the next problem, maybe last, what they have asked, we have to carefully read the question first. We get my charger. Okay, yeah. Sorry, I had to get my charger. Okay. So the problem is saying that an impulse steam turbine has several number of pressure stages. So basically, this is a pressure compounding turbine. Okay, each having a row of nozzles and a single ring of the blades. Okay, the specific work produced by the turbine per stage is 52 kilojoule per kg. So they have provided the specific work and what it would be. The specific work is defined as the rate of work produced divided by mass flow rate. Okay, so the ratio of W dot by m dot, they have provided the value as 52 kilojoule per kg. Then the velocity of steam leaving the nozzle, they have provided a value of that. Velocity of steam leaving the nozzle. So what it would be? The Vs value, the Vs1 value they have provided as 345 meter per second. Then the supply of steam to the first stage is at 2.5 megapascal and 300 degrees centigrade. Okay, so the inlet conditions they have provided: inlet at 2.5 megapascal and 300 degrees centigrade. Let me write it more clearly: 2.5 megapascal and 300 degrees centigrade. Okay, so the specific enthalpy at inlet at this condition H1 they have given as 3009.6 kilojoule per kg. Okay, and at the condenser pressure means at the exit or the outlet condition they have also provided at 0.07 bar. The exit enthalpy H2 is 2033 kilojoule per kg. Okay, then determine the following questions 8 to 10 based on the following data. Okay, and we have to assume the equal stage efficiency and equal work done for each stage. Okay, so as the problem 9, we have to determine the blade efficiency with this provided data. So for the solutions, I will choose different color pen. Okay, so sorry for the interruption. Okay, so like this, we are having this H2 and H2, H1 and H2. So based on that, we can calculate the enthalpy drop. Enthalpy drop delta H would be H1 minus H2, and it would be 3009.6 minus 2033. The value is 976.6 kilojoule per kg. Kilojoule per kg. Now, what we have to do as the first part, we have to determine the blade efficiency, eta B, and the expression we know is that it would be the ratio of power divided by kinetic energy. Extend the thing is that W dot divided by half m dot Vs square. If we will simplify it, then we get 2 into W dot by m dot into 1 upon Vs square. So this value we are having here, the ratio of W dot by m dot, we will feed it here, and this Vs1 we are having here. So after putting these values here, this expression, we will get eta b 2 into 52 into 1 by square of 345, and to convert into the percentage I will multiply it by 100. So when I will simplify it or solve it, then I will get the value 2 into, okay, so as it is in kilojoule, I also have to multiply it by 1000 to make it to joule, or 52 to 1000 joule per kg. Okay, the value will come out to be 87.37%. So the answer is 87.37%. So moving to the last problem, problem number 10, what they have asked. They have asked the number of pressure stages for the steam turbine. So number of stages would be, number of stages n would be the total enthalpy drop, total enthalpy drop divided by enthalpy drop in single stage. Okay, and this all value we are having, that total enthalpy drop we have just calculated here, H1 minus H2, the value is 976.6 kilojoule per kg. We'll write this is 976.6 kilojoule per kg. Enthalpy drop in single stage, we have seen that 52. So this value is coming approx 18.78. So we'll pick the higher number. So the number of stages would be 19. Okay. So the number of stages are 19 for this problem. Okay. So these are the assignment problems, and I don't think that I am having the time to solve this problem, because this is quite a lengthy problem. So I will hint you how to do this problem by writing all the given things. So here the steam enters the nozzle at an angle of 20 degree. So here theta value is provided as 20 degree. for an impulse turbine at 30 bar and 320 degrees centigrade. So here the inlet conditions are provided 30 bar and 300 degrees centigrade, and the exit condition, this is inlet condition, and 15 bar is the exit condition. Okay, then mass flow rate is provided. M dot S is M dot is equals to 45 kg per second. Clearly, this is 45 kg per second with the nozzle efficiency of 0.9. The blade is symmetrical. Okay, symmetrical blades. Symmetrical blades. What does it mean? It means that the blade angles are the same. Also, the velocity coefficient is provided. Kv is equals to 0.97, which shows the ratio of the relative velocity at inlet and at exit. The ratio of relative velocity at exit and inlet is 0.97. All these things they have provided to us. So what they have asked for, they have asked first to draw the velocity diagrams and calculate the following parameters: the blade angles, the power delivered by the turbine per stage, and blade efficiency and the stage efficiency. So the velocity triangle would be the same as we have seen in the theory. Then we have to determine the Vs. By this inlet and exit conditions, we would be able to calculate the enthalpy drop. Based on that, we have can calculate the speed, the jet speed at inlet Vs1 is equals to 2 under root delta H. So we will get this value. Then once we will get this Vs1 value, then by the help of trigonometry in the velocity triangle, we would be able to calculate the value of phi, okay, and gamma and phi would be the same. So these things we will calculate. If we do the analysis at the exit, then we would be able to calculate the value of delta also, and by the help of that we can calculate the Vs2 also. So these are the things are quite simple to get if we follow the steps. Then the power for the power delivered, we have the simple formula: W dot is equals to M dot VB Vs1 cos theta minus Vs2 cos that. Until that time, we are having all these things: the Vs1, the Vs2, theta, and del. Okay. You can match the answers. I have already calculated these things. Your power value will come as 508989 kilowatt. Okay. And once we will once we got this power value, then next thing is to determine the blade efficiency. Eta v, we can simply determine the ratio of W dot by half M dot Vs1 square, and this value will come out to be around 87%. Last thing they have asked is the stage efficiency, eta stage, and the expression for that would be W dot divided by M dot into H1 minus H2 enthalpy drop, and this value will come out to be 78%. Here both the values we won't be the same because the blades are not smooth and we are having some uh, coefficient of velocity for that. So I request you to please try this problem, and if you will have any doubt then we can discuss that. Also, we are having these two another problems in the classroom. So please follow the class lecture for them, and if you will have any doubt in those problems, then we can discuss in the next class. So these are the topics we have covered in this class. Initially, I have provided some derivation for the optimum blade velocity, blade efficiency, and the maximum power, and then we have solved this assignment. Okay, problems. If you are having any doubt in this, then we can take, otherwise, we can conclude the session. Okay, nobody is here, I think. So we can conclude this session. Thank you for thank you to whoever have joined. Thank you.